Welcome back. In part 1, we built one machine and it rested on a single idea. To find the cheapest way through a problem, you solve it backward. Start at the destination where the cost left to pay is 0 and walk home. And at every step, you reuse the answer you already worked out for everything downstream. We watched a motorist do exactly that on a road map. From the end H back to the start A. Every intersection earned a gold label. Its cost to go, the cheapest price to finish the trip from there. And we wrote the rule down in symbols. The minimum cost with k stages to go is the smallest over your next control of this step's cost plus the best you can do from wherever it lands you. That is Bellman's recurrence. But the method hit a wall. To handle a real system, we forced it onto a grid, and grids explode. 3 variables, 100 levels each, is already a million cells. Bellman called it the curse of dimensionality. So part 2 asks 2 questions. First, can we ever beat that curse? It turns out we can, when the system is linear and the cost is quadratic. The whole problem collapses to a clean, closed form with no grid at all. Second, what if we stop chopping time into chunks and let the step shrink all the way to 0? The backward recurrence becomes a single, elegant, partial differential equation, the Hamilton-Jacobi-Bellman equation. Let's build both. Start with the first question. We're going to pick a very particular kind of problem and get our reward in closed form. It's called a linear regulator, and the picture behind the name is simple. Think of a controller whose only job is to push the state back to 0 and to do it as cheaply as possible. A thermostat hunting the set point, a rocket killing a wobble. The state has drifted and we want it home. Now, cheap means something specific. We charge a quadratic price for 2 separate cents. 1. How far the state strays from 0. That's the term x transpose qx, with q a weight we choose. 2. How hard we shove to fix it. That's u transpose ru, with r the price of effort. Square both, add them up over every step, and add one last charge on where the state finishes. That whole sum is the cost j. The system itself is linear. The next state is a matrix A times the state now plus a matrix B times the control. No curves, just A and B. And here's the seed we'll grow everything from. At the very last instant, with nothing left to decide, the cost to go is just that final penalty, 1/2 x transpose hx, a quadratic form in the state. Hold on to that shape. The entire derivation is about to show it never changes. Watch the shape survive. We'll solve the last stage and then let induction do the rest. With one step to go, the cost is that final quadratic plus the price of this step's control. We want the control that makes it smallest, so we do the obvious thing. Take the derivative with respect to u and set it to 0. The algebra hands back a single clean line. The best control is minus the quantity r plus b transpose pb inverted times b transpose pa, all multiplied by the state. Call that matrix F. The optimal control is just f times x. Is it really a minimum and not a maximum? Check the second derivative. R plus b transpose pb. R is positive definite. The other piece is positive semi-definite, so the sum is positive definite. Genuine minimum. Good. Now the punchline. Substitute that best control back into the cost, and what comes out is, again, 1/2 x transpose some new matrix P times x. The same quadratic shape we started with, which means we can do it again and again, peeling one stage backward each time. P feeding the next F, F feeding the next P. So 3 things fall out at once. The optimal control is a linear function of the state, a feedback gain, exactly the rule we wanted back in part 1. That feedback drifts from stage to stage, even when A, B, Q, and R never change. And the minimum cost for the whole run is 1/2 x naught transpose P x naught. No grid, no curse, just a matrix swept backward. Does it actually work? Let's run Kirk's own example and watch. A second order system, two state variables, with these fixed matrices A and B, these weights Q and R, and a 200 step horizon. We start the state at 2 and 1 and ask the recursion for the gains. Look at the feedback gains first. Sweeping backward from the end, they settle almost immediately onto a constant pair, minus 0.55 and minus 5.97. Flat for the entire middle of the run. They only bend in the last stretch, near the final time, because the end penalty here is switched off. That flat steady value is a gift. For a long horizon, you could throw the schedule away and use one constant gain. Now the trajectory. Feeding that feedback law back into the system, the control spikes early, a hard shove of about +7, and the two states starting at 2 and 1 are driven smoothly down. By step 100, they have essentially reached 0 and stay there. That's the regulator doing its one job. No grid was ever laid down. A single matrix formula evaluated backward once steered a real system to rest. The curse is beaten for this whole linear quadratic family. Now the second question, the daring one. So far, time came in discrete stages. What if it doesn't? What if the clock is truly continuous? The system now evolves by a rate of change, x dot equals a, some function of the state, the control, and time. The cost is a final term plus an integral of a running cost g accumulated from now until the final time. We define the star of the whole show, j star of x and t. In words, standing at state x at time t, it is the cheapest possible cost to finish the job from here. The smallest total over every remaining control. This is the embedding idea. Instead of one problem, we quietly consider a whole family of them, one for every starting state and every starting time, and solve them all at once. Here is the move that should feel familiar. Split the remaining trip into two pieces, a tiny first slice of length delta t and all the rest. The principle of optimality, the exact same principle from part 1, says the best you can do is the cost of that tiny slice, plus the cost to go from wherever the slice leaves you. Written out, j star at x and t equals the minimum over the control in that little slice of the running cost across it plus j star at the new state a moment later. That is Bellman's recurrence again, only now with a continuous clock, and we are about to shrink the slice to nothing. This is the moment the two worlds fuse. Take that recurrence and let delta t go to 0. The trick is a Taylor expansion. The future cost to go j star a moment later is approximately the cost to go now plus its slope in time, j star sub t times delta t plus its gradient in the state, j star sub x, dotted into how far the state moved. And how far did the state move? Over a tiny step, it's just delta t times the rate of change a. Now substitute and watch the cancellation. The cost to go now appears on both sides and drops out. Every surviving term carries a factor of delta t, so divide it through. And then let delta t fall to 0. The discrete ladder of stages dissolves into a continuum. The sum becomes smooth. And the backward recurrence, the very equation we just recapped from part 1, turns into a single line. 0 equals the time slope of the cost to go plus the minimum over the control of the running cost plus the gradient of the cost to go dotted into the system's motion. That is the Hamilton-Jacobi-Bellman equation. Its boundary condition is simply that at the final time, the cost to go is the final penalty. We give that bracketed quantity a name, the Hamiltonian h, and the equation reads even cleaner. 0 equals the time slope plus the minimized Hamiltonian. It is the continuous time twin of Bellman's backward recurrence. Same idea, no grid. This equation deserves to be solved by hand at least once, and slowly, because the trick is the whole subject. Take the simplest system that still has every part. X dot equals x plus u, and the simplest cost, a quarter of the final state squared plus the integral of a quarter u squared. So the running cost is a quarter u squared and the motion is x plus u. Build the Hamiltonian. A quarter u squared plus the cost to go gradient times the quantity x plus u. Set the derivative in u to 0. 1/2 u plus the gradient equals 0. So the best control is minus 2 times the gradient. The second derivative is 1/2, positive, so it's a minimum. Now the step the first cut of this video skipped, and it's the important one. Substitute that best control back into the Hamiltonian. A quarter of minus 2 gradient squared is gradient squared. The gradient times x minus 2 gradient gives gradient x minus 2 gradient squared. Add them and the squared terms collapse. We are left with minus the gradient squared plus the gradient times x. So the equation becomes 0 equals the time slope minus the gradient squared plus the gradient times x. Now we guess. The cost to go is 1/2 k of t times x squared. That gives us 3 pieces. The gradient is kx. The time slope is 1/2 k dot x squared. And the gradient squared is k squared x squared. Substitute all three. 0 equals 1/2 k dot x squared minus k squared x squared plus k x squared. Every single term carries an x squared. Factor it out. And here is the magic. This has to hold for every possible state x. The only way a bracket times x squared can be 0 for all x is if the bracket itself is 0. So the x squared divides away and what remains is a pure equation in k alone. 1/2 k dot minus k squared plus k equals 0, with k equal to 1/2 at the final time. That is the Riccati equation. So what kind of equation did we just earn? Look closely. It has k and its first derivative k dot, so it's first order. But there is one troublemaker, that k squared. The square makes it non-linear, and being non-linear is exactly what makes it a Riccati equation. Where did the square come from? Trace it straight back. The k squared came from the gradient squared, and the gradient squared came from squaring the control, that quarter u squared penalty we started with. The cost of effort was quadratic, so the equation for k is quadratic. Kill the square, pretend the term isn't there, and you just have k dot equals minus 2k, a plain exponential. The square is the entire personality of the problem. Now let's actually solve it. The equation separates and integrates in closed form. K of t equals e to the t minus t over e to the t minus t plus its reciprocal. Don't memorize it, just watch the shape. At the final time, k is 1/2, exactly as the boundary demanded. Look earlier and k rises, leveling toward 1. Now put real numbers on it. Take a 2-second horizon and start the state at 1. At the end, k is 1/2. At 1 second, k is about 0.88. At the start, about 0.98. Feed that into the control. U star equals minus 2kx. And the state obeys x dot equals 1 minus 2k times x. Early on, k is near 1, so the rate is near minus 1. The state decays hard from 1 down to about zero point 0.4 by the 1 second mark. Near the end, k falls to 1/2, the rate hits 0, and the trajectory coasts to rest. And if we let the horizon run to infinity, k just sits at 1 forever. The loop becomes x dot equals minus x, and the system is stable. That is the whole move. Guess a quadratic cost to go, then verify. Everything we just did by hand survives, almost word for word, when the state becomes a vector and the system becomes matrices. The same 5 steps. The system, x dot equals ax plus bu, the same quadratic cost. The Hamiltonian, 1/2 x transpose qx plus 1/2 u transpose ru plus the gradient dotted into ax plus bu. Step 1. Minimize. Derivative to 0 gives the control, minus R inverse B transpose times the gradient. Set it beside the scalar answer, minus 2 times the gradient. The same shape dressed in matrices. Step 2. Substitute it back. The Hamiltonian collapses to 1/2 x transpose qx minus 1/2 gradient transpose B R inverse B transpose gradient plus gradient transpose ax. Step 3. Guess. The cost to go is 1/2 x transpose k of t x with k a symmetric matrix. Its gradient is kx, the matrix echo of k times x. Step 4. Substitute the guess. You get 1/2 x transpose k dot x plus the q term minus the k b r inverse b transpose k term plus x transpose k ax. Step 5. The matrix version of dividing out x squared. A quadratic form only ever feels the symmetric part of its matrix. So x transpose k ax equals 1/2 x transpose the quantity ka plus a transpose k x. Now every term is sandwiched between x transpose and x. Demand it hold for all x, strip the sandwich away, and out drops the matrix Riccati equation. Minus k dot equals q minus k b r inverse b transpose k plus ka plus a transpose k, with k equal to h at the final time. Set it beside the scalar version and it's the same equation wearing matrices. Half k dot becomes k dot. Minus k squared becomes the kb r inverse b transpose k term. Plus k becomes ka plus a transpose k. And we have already met its shadow. Remember the discrete example? The gains that settle to minus 0.55 and minus 5.97? That backward p recursion is this very equation sampled in time. Continuous k, discrete p, 1 hero, 2 guises. Step back and see what we've earned. The Hamilton-Jacobi-Bellman equation is a necessary condition. Any optimal cost to go must satisfy it, but it's also sufficient. If you can find a function that solves it, you haven't just found a candidate, you found the true minimum cost. That's rare and precious. The catch is honesty. In general, the equation has no tidy solution. You reach for a computer. The guess a quadratic move only works because the dynamics were linear and the cost quadratic. That special class is exactly the linear regulator. But here is the image to leave with. In part 1, the discrete dynamic programming recurrence led us to a backward sweep of matrices. In part 2, the continuous Hamilton-Jacobi-Bellman equation led us to a backward sweep of k. And there is a third road, the calculus of variations, waiting in chapter 7. And for linear regulator problems, all 3 roads arrive at the very same place, the Riccati equation. All roads lead to Riccati. So here is both films in one breath. To steer anything optimally, solve from the end and reuse the cost to go. And when the world is linear and the cost is quadratic, that cost to go is a simple quadratic bowl, and the optimal rule is plain linear feedback. The grid is gone. The curse is beaten. See you in chapter 7.